Hello everyone, I'm Sister T, and here's our second period of AP Mechanics C. Okay, so before I have today's review, I want to correct a mistake that I made in last time's video, and which I'm really sorry for you guys. I just hope that you guys won't misunderstood it. So it's around about 7 minutes or so. I say that it should be that it does not obey the conservation of mechanical energy. I was talking about perfect inelastic collisions back then, and we will cover that probably very soon. Okay, so in the last time's video we talked about those two equations, and we see how kinetic energy can convert it to potential energy in some examples. And we talked about conservation of mechanical energy when only conservative forces are acting on the object. And we get to know the definitions of gravitational potential energy, also elastic potential energy. Let's solve the questions that I left for you guys in the last time's video. I want you guys to find specific values of those quantities. I mean, where their special values exist, right? So before we get to discuss that, I need to clarify one thing. And so the maximum compression that of this spring, we will just call it minus A, relatively to the 0 point that we set, which is the original length of the spring. And of course, the maximum point that this spring can be stressed is also point A, right? Since if it is stressed further, let's say here, further than point A, then P will not, potential energy of the spring will not be conserved, right? And it cannot happen. So we will just use minus A and A to represent the beginning point, also the maximum displacement of the spring. Okay, when I compress the spring to the maximum extent at minus A, it is at rest, right? So all its energy is actually the elastic potential energy. So at this point, PE actually reaches its maximum. So when I release my hand, it begins to move in this direction, right? It is accelerating. So we can know that the acceleration of the is positive, right? And according to the Newton's second law, written as this, we can also know that F is pointing this way as well. We'll use an arrow to represent it. Okay, so as we stated, then it is accelerating, it gains more kinetic energy, right? So it is actually experiencing a conversion between potential energy to kinetic energy. Okay, so its velocity is increasing, and what happens when it gradually reaches the point of x0, which is the original length of the spring? Well, will it still have the elastic potential energy? As we know that the way to calculate it is this, and as x0, there is actually no displacement since it's at its original point. So PE at this point should equals to 0, which means that all the PE has been converted to kinetic energy. So at this point, PE equals to 0, but we can also say that kinetic energy is maximum, right? Okay, so when the kinetic energy of the spring is at the maximum, the velocity is absolutely the maximum, right? And since we know that A is the derivative of velocity, so when velocity is at its maximum, A equals to 0, right? And use this equation again, the force will also be 0. Okay, so when it is moving during the part from x0 to A, what happens to its velocity? Its velocity will decrease, right? And the acceleration will be negative. So it is actually pointing to the left. And since we know that the force is in the same direction as acceleration, so the force is pointing to the left. Okay, so in this part, we also experience a conversion between kinetic energy to potential energy, since now we have displacement again relative to the x0 that we set, right? So at point A, just like the minus A, PU is the maximum, since A is the maximum displacement this plane has, right? So when P is maximum, then there's no kinetic energy. The velocity will be 0. Okay, so and as I said, the displacement is the maximum, so the force will also be the maximum. And so does the acceleration. And to be more specific, the changing process of potential energy and kinetic energy can be draw in graph like this. Just help you guys to understand, okay? Now let's have a little exercise. For A, it wants us to find the friction on the back of gravel and on the box. Okay, so actually you can see here that they are not moving relatively, so there's no friction between them. But it may not be the same for the box and the surface, right? Since although it is at equilibrium state, but it has different forces pointing at it. So here is a three-body diagram that I draw. I forgot to draw. I only draw the forces that are acting on the x-axis. Okay, so it has a force, let's just call F1, pointing to the right, exerted by the weight of the concrete, and it should equals to the static friction, right? So it's easy for us to calculate the magnitude of the friction. It should equals to the weight of the concrete. And that's the answer for part A. So part B, at start, there is no kinetic energy, right? So it will just be 0. But what about the potential energy? Potential energy should be how much it descends, right? Before it has that much gravitational potential energy, but after it changes its height, it gets smaller. So we'll just write it is actually should be delta potential energy here. Right? And it should equals to K final plus U final plus. But you see, I just move it here, so they will just mean the same. And we want to calculate the K final, right? So it should equals to, so the force, so the work done by the friction should be the weight of the box, the coefficient, and multiply its displacement, since when it is moving down for 2 meters, it is also moving to the right for 2 meters. They are on the same string, right? Okay, to correct this, it should be written as okay, so that's the correct form, right? And we can now yell the value of velocity, which should be 2.99 meter per second. Okay, so that's all for our little exercise. And the last point that I want to discuss is the definition of power. And this is the equation for its definition, and it has a unit of watts. We use capital W to write its unit, and there are two prevalent units that we use. One is kilowatt, and second is, and it equals to 10 to the power of 3 watt, and it equals to 10 to the power of 6 watt. Those are common used. And there's another unit called horsepower. You may see it in the exercises as well. Okay, so that's all for today's video. I hope you guys enjoy it, and if you have any questions, you can just leave your comments there and we will check it. And thank you for listening. Bye!